Here we go, and welcome to Chapter 8. Day 1 for us. Chapter 8, really out of our textbook, if you're looking at it anyways, which you should be doing on a regular basis, is entitled Confidence Intervals. So let's go right into some information and some reminders. When we took the data at the beginning of the year, we took people's heights, and then this was their heights. So what we're going to do for today is let's consider this the population of heights. So we're going to make sure that this is the actual, if this is our whole population of data, 71 data points, realistically this up here shouldn't be x bar, right? That should now be considered mu. That's my population average. And then I already changed it here. Instead of S, it's sigma. So sigma is the standard deviation of the population. Mu is the average of the population. So the other thing I want us to assume for today is let's assume that population height is normal. So we're going to say that this is close enough to normal for our sake for today. So in doing so, what is if this is our population, what's the probability that a randomly selected person will have a height over 72 inches, all right? So let's just recall how we do that. There's a normal distribution. Sigma is known. So I'm going to use z equals x minus mu over sigma. I'm going to show that formula every time, which is statistic minus parameter divided by standard deviation of the statistic. Insert numbers, 72 minus 69.3482 divided by 4.5172. Again, those numbers, the mean, we said this was the mean of the population. That was the standard deviation of the population. So this will give me a z-score of 0.587. And then on a normal curve, z centered at 0, 0.58 is somewhere right about here, 0.587. And what's probably the randomly selected person is over 72 inches. So then from there, then I go to my applets that I have online, and I'm going to go down to the normal applet. And it tells me that that area right there is 0.2786. So then that will mean that there is a 27.86% chance that an individual will be over 72 inches tall. All right, so that's what we did right there. So when we enter that information, 72. Now you could have also put in here, either enter this information, or when it comes up automatically, this is 0. Standard deviation is 1. Instead of the x of 72, we could have put in 0.587, the z-score that we have, and it would give me this same area. All right, and then again, the important part is then an interpretation statement. So you would write a sentence that would say something like 27.86%. There's a 27.86% chance that a randomly selected person is over 72 inches tall. So the second half of this, though, the question was, what if it's a random group, a randomly selected group of 5? So here, what's the probability that a random group of 5 people will have an average over 72 inches? All right, let's remember, now we're talking about a sampling distribution. And since the parent population I said was normal, that means my sampling distribution is normal. So since the distribution is normal. The sampling distribution is normal. And that is not the central limit theorem. The central limit theorem would be if the sample size is large enough, which is over 30, then the sampling distribution is normal. So make sure in a case like this, you're not saying because of the central limit theorem. This is just a known principle that if a distribution is normal, then the sampling distribution of averages is also normal. And then we recall that these two things are true. So the standard deviation of x bars is equal to the standard deviation of x. So it's going to be centered at the same place. And the standard deviation, so the average of the averages is equal to the original average. The standard deviation is equal to the standard deviation of the original one divided by the square root of n. So that belongs in there. And then if we were to go back and look, so this number that we had was 4.5172. That was the standard deviation of my population. We're going to be doing it out of 5 people. That's the standard deviation of the sampling distribution. And that's what I have drawn over here. So original average. There's my new standard deviation that you'd have to change because it's now a sampling distribution. 72 is my boundary point. And there's my value. All right. So that means there is a 9.47 or 46, doesn't really matter. You could round up or round down because it's halfway between. The 5 is exactly half, so it can round either way. Percent chance a group of 5 people will have an average of 72 inches height or more. So 72 inches or more. All right, so what I actually did is I went ahead and used the random number generator online from 1 to 71, and it selected 5 numbers, 7, 17, 28, 8, and 57. I went to the spreadsheet of values, and I went to row 7, and I chose that one, and that person's height was 73. I went to row 17, that person's height was 68. I went to row 28, and that person's height was 72. So again, the random number generator gives me these numbers, and then I have to go and look for the corresponding heights. Number 8 was 80, number 57 was 67. So these are the 5 inches, and these have an average of 72. That's why I selected 72 for the previous problem. So we said there was a 9.46% chance that a random group of 5 people will have a height of 72 inches or more. All right, and this was based off of the random group I took. What we're going to do next is say, yeah, but what if we don't know the population average? So let's say we took a sample of 5, it gives us an average of 72. How do we know 72 is a reasonable estimate? All right. Ultimately, the answer will always be we don't know. So we always have to go back and say, did I use proper procedure? Did I use an actual random number generator? If I did that actually then randomly select people from whatever population of interest I am caring about? But, so again, considering the population that we had, the sample we took, now we're going to think about it working it backwards. Let's take a sample and see if we can make some generalizations about a population based on these estimates. So I redid this, and now since my average of my sample was 72, I'm going to pretend that that's the mean of the population. And since we knew this, we're going to have to, if we know sigma, which we did, we're going to say that we knew sigma. So in the standard deviation of the sampling distribution was this number. So now I have it centered at 72 instead of what it originally was, 69 point something. But we're going to look at this and say, all right, well, How can I, this is a single point estimate right here, 72. Right. Which is not a great way to estimate the mean. So what we're going to do instead is say, well, let's create a confidence interval. And if I do a confidence interval, all right, so we've got 1, 2, and 3 standard deviations down. If I do this, and again, we know that the sampling distribution is normal because we were told that the population distribution is normal. Since the sampling distribution is normal, if I were to repeat this process many times, I would assume that about 95% of the X bars, so 95% of the X bars will be within 2 standard deviations. That's the empirical rule. Because again, if it's normally distributed, all right, this was my sample average, 72. So we're going to say, if this were the actual average of the mean, and I were to repeat this process many times and take lots of samples of size 5, I would expect 95% of the X bars to be within 2 standard deviations. So 2 down is going to be, just under 68. Because that's, 2 sigmas, so 2 times 2 is 4. 72 minus 4 is 68. 72 plus 4, right, gets you up to about 76, so somewhere right up here. These numbers are not listed as standard deviations. They're just made as reference to values going up. So this number here is not 2 standard deviations. We can see it's 2.5 up. So these are just going up and down by 2.5. Standard deviations 2. So 72, 74, 76. Should be right about there instead of at the 75. But either way, 95%. So, to do this, what we're going to be doing is then this is what it's called, is constructing a confidence interval. There should be brackets on this because it's an interval of values. We're going to take X bar, which is this average of my sample, plus or minus the Z. Now the Z will depend on my confidence level. So if I want to be, if I want to have a 95% confidence level, we're going to actually find out here pretty soon that my Z is actually 1.96. Now, yes, we said it was 2 with the central limit theory, with the empirical rule, but we're going to get a little bit more precise now in finding Z values. If I wanted to be 90%, I believe Z will be 1.28. Now these are rounded, but you'll get the idea when we get to there. But let's define some things. So this is a confidence interval formula. X bar plus or minus Z times, and this should be sigma over the square root of n. All right. Sigma over root n, that's the standard deviation of the sampling distribution. All right. This is also called the standard error. So the standard error is equal to sigma over the square root of n, which is the standard deviation of the sampling distribution. When we're doing confidence intervals, we'll call it we'll call it standard error. When we're just talking about sampling distributions, we'll call it the standard deviation of the sampling distribution. The point estimate in my thing up here, that's my X bar. The interval estimate, that will be the whole thing that I get when I'm done. And I already talked about confidence level, that's whatever my confidence level is. And then these are the same thing, margin of error and the error bound for a population mean. You'll typically hear me call it margin of error. So margin of error is whatever I'm plus or minus. That's my margin of error. That's my margin of error. Just this piece here, that's my standard error, SE and ME. All right, and then whatever the statistic plus or minus the margin of error, that will give me my interval. So let's actually take a look and see what that would be like. So I'm going to show you from the online applets what we would start plugging in up here when you first get logged in. If I choose 0 and 1 and I put in 0.95, what we're going to see is, well, that's telling me the 95th percentile. Well, if that's 95th percentile, that means the area up above is 5%. And that would not be the number I want to choose. And the most common mistake, I'm showing you this here as a very common mistake. The reason why it's a mistake is a 95% confidence interval is from marker to marker, I want to be 95%. I don't want to be 95th percentile. So 95th percentile is 95% of the data is at or below this value. A 95% confidence interval is an interval centered on the mean that includes 95%. So when we're using the normal distribution applet online and pretty much any technology tool that we're going to use, we just have to be smarter. And this is another reason why I want you every single time to draw a picture. Because if I were to draw a picture that had a 95% in the middle, 95%, that means the two tails together are 5%. So this is 2.5%, and this is 2.5%. And the reason why we're going to do that, so then we get down to this third one. This would be the correct way of doing it. The mean is 0. This would be on a z. 0.025 above tells me that, so that area is 0.025. That's what I want for a 95% confidence interval. Gives me well, here it says x, but since I know this is 0 and 1, so that's a standard normal curve. This is z. All right, so the z right there for a 95% confidence interval is 1.95996. So I'm going to round that to just 1.96. So for as much as I've been telling you don't round anything, it's okay to round your z to 2 decimal places. That's pretty common amongst statisticians, and yourself being one of those. So here we go. Constructing the confidence interval. Make sure I get that right. Bracket, bracket. Here are my brackets. X bar plus or minus z times sigma over root n. From that data, 72 was my average from my sample. 1.96. This was the sigma that was given as part of the population from one of those first slides, divided by the square root of 5. All right. When I put these numbers together, I get this value. So this is my margin of error. As we approach any type of election series, you're always thinking when they say plus or minus 3%, they're talking about there the same thing. It's margin of error, which we'll get to in the next, probably chapter 8, day 2 or day 3, we'll do proportions. But once I do it, plus or minus, so I'm going to do 72 minus that to get 68.0405, 72 plus this to get 75.9595. And then lastly, I'm going to write my interpretation statement, and I'm going to say I am 95% confident the true mean height for our population is between 68.04 inches and 75.96 inches. Another way that you could interpret it would be, instead of saying it this way, would be if I were to repeat this process many times for thousands of samples of size n, or of size 5. So if I do this thousands of times, I would expect 95% of the intervals that I create would contain the true mean. Now in this case, we knew the true mean, it was 69 point something. So we knew it was in that interval. So when I started out and said, was 72 a reasonable estimate based on my sample size and wanting to be 95% confident, it was, because it actually captured the true mean. It does not matter. Like if the true mean were 68.1, 68.1 is in this interval. So this would also be a reasonable estimate. Since we don't often know the true mean, we won't know where it falls in there, but what you cannot say is, well, it barely captures it. Don't say that. It's either in or it's out. If it's in, it's good. If it's not, then it's out. And that's just simply, it doesn't matter how close it is in or how close it is to not being in when we actually are knowing this value. All right, so this is the most common way of interpreting a confidence interval. What you do not say, which will be 100% wrong every single time, would be there's a 95% probability that the true height is in there. And that would be incorrect. Either the height is in or it's out. So it's either 100% guaranteed in or it's 0% guaranteed out. But you can't say there's 95% probability that the true mean is in this confidence interval. We say I'm 95% confident that the actual average height for our population is somewhere in this range between 68.04. Online, if you go to this applet, and you're going to actually do this for some of what you're going to reply to for credit for attendance and then also just credit for participation, you're going to go to this website. But what I did is I created here, and let me just zoom in on these. So this one was for, when you go to that website, 95% confidence interval. Here's my parent population, if we knew it was normally distributed. My sampling distribution is red. You'll notice it's narrower. I did samples of size 5, and then I hit sample 25 times. And then these would be, if this black is the actual population of parents, parent population, it's going to randomly select 5 data points. It's going to find an average right there, and it's going to do x bar plus or minus z times sigma over root n and create this confidence interval from there to there. And you can actually see, because we know this parent population's average is mu, that the x bar, while it's lower than mu, the interval itself captures mu. This one also does, this one does, but then, they actually all captured the mean. All right, so if we were to repeat this process, again, thousands and thousands and thousands of times, we would find that this would be about 95%. Because if I did repeated samplings, all of size 5, repeated, approximately 95% of those intervals will contain the true mean. All right, but then for each of these, even this one here, you'd say, I am 95% confident that the true mean lies between here and here, whatever those endpoint values are. And this is demonstrating that when we know the mean, we can actually see that this is true. In many cases, though, we won't know the means. We'll be actually trying to estimate what the mean is in that interval. All right, so I'm going to move across here. What did I do this time? I increased my sample size to 15 and did a sample. And notice, so over here on this one, that was the parent population. This is the same parent population, but because of scaling, what happens is because this is a larger sample size, the standard deviation of x bars will be now sigma over the square root of 15 instead of over 5. So I'm dividing by a larger number, which makes it narrower. And since all of these underneath have a height of 1, an area underneath the curve of 1, right? Every curve has an area under 1 for a probability density function. When I make it narrower, it has to get taller. So it becomes taller than the parent population. But again, this parent population was the same as this one back here in the previous example. But now my sampling distribution is narrower, and then obviously it becomes taller. So now when I'm collecting data, and I'm collecting 15 data points, it's going to be harder to be away from this value because I'm reducing the variability. And I look at this, even that one, but I ended up again, unusually, but all of them hit, all 25 hit. But if you keep hitting sample many times, it'll give you a running total, and you should start to approach 95% once you've, sampled 10,000 don't actually do that, right? And then third one over here, narrower yet, because now I'm dividing by the square root of 30 for my sampling distribution. Sigma sub x bar equals sigma over the square root of 30, dividing by a larger number, narrower. And then there it'll actually show you, oh, look at that. All right, that one missed. All right, so here's what I want you to do. You're going to go to that website. Right, there it is. If you haven't written it down, do that now. But then you're going to go back to here and get your slider adjusted to 30 and do a couple sets of sampling of 25. And then what I want you to do is look at this. All right. When you move this slider up to a higher confidence level, what happens in the graph? And you'll see something happen. If you take this slider and do it to a lower confidence level, what happens in this graph? So you're going to basically write two sentences using correct mathematical terminology for what we've been talking about with confidence level and interval width. So you're going to talk, so if this increases to a higher confidence level, talk about what goes on with the interval width. If this goes to a lower confidence level, talk about what happens in the interval widths. And you'll see, as you manipulate this, you'll see things change over here. So you're going to send that to me in an email, and it needs to be sent before our next class meets. So make sure you get that done. But that's not all. Stay tuned till later in the video for something else. All right. But again, complete sentences. Then what happens? Well, what happens if we don't know the population standard deviation? Right? So first it was, well, what if we don't know mu? Then we use x bar to estimate it, and then we make an interval to estimate it when we knew the standard deviation sigma. But now, what if we don't know the population standard deviation either? If we don't know the population standard deviation sigma, we're going to estimate it using S. All right? Sometimes we'll see S of x. S of x is the sample standard deviation. And since we're no longer using sigma, we cannot use z. So we cannot use the standard normal curve anymore because, well, it only works if we know the population standard deviation. So what do we use? Good question. We're going to use what's called the student's t distribution. I think I may have referenced it at some point, but it's called students because it was originally created through work done by William Gossett. William Gossett was working for Guinness Brewing Company in England. England? I think so, yes. And because of his job there, they would not allow him to publish things under his name, so he published them under the pseudonym Student, and it stuck so much to the point that we still call it the student's t distribution, or sometimes just the t distribution. Here is the student's t distribution. So let me fix this up here. That's a square root. Got my brackets on here. And here's my interval, x bar plus or minus. So instead of z, it's now t. And our book uses alpha over 2, and I'll explain that. And then s over the square root of n instead of sigma over the square root of n. The relationship between the z and the t is this. If this is a standard normal curve, the student's t distribution is going to be still mound-shaped, but it's going to have more data out on the tails. It's going to be less condensed around the middle. And there's many t distributions, and it all depends on what's called df, which is degrees of freedom. Degrees of freedom are equal to n minus 1. N minus 1 So n is the sample size. So for us, our sample was 5, so it'll be 5 minus 1. So we'll have 4 degrees of freedom. The larger n is, the more degrees of freedom there are, and it will actually get taller and closer to a z curve. And what we see happens down here when I get all the way to the bottom of my, so df, 4 is where we will be, but if I have more and more in my sample size, 1,000, pretty much after 1,000, we just say it's the same as a z. And if we did see 95% earlier, 1.960, that's the z value for a 95% confidence level. All right. The alpha over 2 confidence level plus alpha equals 1. So if my confidence level is 95%, my alpha is 5%. Alpha over 2, that's when we split we split the tails in half. We said, all right, 95% is my middle. My tails are the remaining 5%, each of which is 2.5%. So that's alpha over 2, because it's 5%, 2.5 on each end. So when we're talking t, 0.025, that's the alpha over 2. And that's if this is for one tail. If it's 2 tails, the 2 tails together is 5%, 5%. So you can see a one-tailed 2.5% and a 2-tail 5% are the same value. Because if it's one tail, 2.5%, 2 tails, that would be 5%. Or also down here at the bottom. So I like using the t-table for getting this information. Can be found in your book, but there's another way to find it, and we'll take a look at that online in a second. All right, so here was my data. I took these 5 numbers, I plugged it into StatBlue for histogram, and it gives me this information. N is 5. The average of my sample is 72, and now it's a sample, right? My S is the standard deviation of that sample. So I did these 5 numbers. This was my average. That was my standard deviation of these. And what I'm going to do then is plug them into this formula. So let's add my stuff back in here. This is square root of n, so that's square root of 5. Brackets here, brackets around everything there. I don't know why my 72 is off my page, but that's 72. X bar was 72, S was 5.1478, N was 5, so square root of 5. And then this, the t value. We're going to look at my t table. Degrees of freedom is 4, so I'm going to go across the 4 degrees of freedom until I intersect with confidence level. And I find that that happens right about here. Right there. So across 4, that's in the 95% confidence interval column, or you can also think one-tailed 0.25, or it's the 2 tails, 5%. So this, if it's 2 tails, that's alpha. 2.776, that's the number that goes here. We enter all this in, I get these 2 numbers, and then I would say I am 95% confident that the actual average height of students who took this survey will be between 65.6 and 78.391 inches. Go back, listen to that again, write it down, and get in the habit of writing that down almost exactly the same way every time. That is the best way to learn how to do a confidence interval and interpret it the right way. So if you go to the applets, there is also one on the list, and it's just called t.html. And this is what comes up. This is degrees of freedom. So that little symbol is the degrees of freedom. So for what we did, 4 was our degrees of freedom. That's why this is here. Once you do this, it'll create a graph. And it shouldn't be X, this should actually be T. And then my area of my tail greater than 0.025, that's the one-tailed, right? That was T, that's alpha over 2, will give me just this area up here. 0.025 gives me the corresponding T value of 2.77645. All right. So second thing you're going to do now is we created two 95% confidence intervals. So the second thing I would like you to type in that email that you're going to send to me before our next class starts so that you can get both attendance and participation points for it is I want you to look at the two intervals. Tell me which one is wider. And then if you can, explain why you believe that one is wider than the other one. But we have all the numbers were there. You can go back and look at it, and you can determine which interval was wider. And then as that goes, do you know why that one particular interval was wider than the other one for the two 95% confidence intervals we created? So there you go. There's our welcome to confidence intervals. By this time, you should be pretty well versed in our textbook online and going and finding where all of the practice and homework is. Those are all links on the left side of your table of contents for Chapter 8. Working through all of those odd problems because they are all the numbers that are answers are available for it. So taking time and doing that, yeah. See you next time.